All right, good morning, ladies and gentlemen, future presidents, and other important leaders of society. So, again, welcome to Physics for Future Presidents. As I said last time, I will typically pause here in the beginning of each class for 5-10 minutes, or as long as I have patience, or if you have questions, to answer anything that you may want to bring up right here in class. Hopefully, physics-related or science-related, technology-related, or any other important issues of the day. Or perhaps class-related in terms of either educational technology or mundane things with B courses and such. So let me first see if you have any questions for me right now, and then I'll start on my spiel. Oh, let's start in the bottom. Yes. Okay, so there was a question about difference between chemical energy and nuclear energy. Great question. Let me defer it, because we'll jump right into it when we start. Is there a way to, so the question is there a way to make energy transformation processes more efficient? Remind me again in about half an hour. So yes, we will talk about energy storage, we will talk about energy transformation efficiencies, and what limits that. I think that, and I'll come back there. Yes? So the question is, you read that as we evolve, right, or as Earth rotates around the sun, or as we evolve, all of the energy ultimately will be converted into heat. And the question is whether this has to do with global warming. I think the answer is yes and no. So ultimately, and that actually I put on one of the slides, this is one of the definitions of energy. Heat is perhaps one of the most fundamental demonstrations, or most fundamental forms of energy. Heat is motion of elementary small particles that compose matter. We'll talk about it next week. So very generally, heat is kinetic energy, motion of small stuff. And for pretty much every energy transfer process ultimately results in some kind of motion. Most of we here on Earth are trying to convert energy into processes useful to humans. You know, we burn energy to live, we use energy to build things, we use energy to propel ourselves back and forth. Ultimately, we stop these processes. You start your car in the morning, you drive, you brake, all that gasoline energy ultimately gets lost and converted into mechanical energy of elementary particles, molecules, ultimately gets converted into heat. So yes, over the evolution of the Earth, over the evolution of the universe, we believe ultimately everything gets converted into a thermal energy. And there's in fact a law there, it's called the third law of thermodynamics, which again we'll discuss next week, which basically says that normal evolution of normal physical processes tend to increase disorder, tend to randomize motion of these elementary particles, which basically says that everything gets ultimately converted into heat. Now the question is, does it have to do with global warming? In theory, it doesn't have to. Again, we'll talk next week about the concept of equilibrium. So in fact, quite naturally, most processes of energy transfer, unless you do something very specific like you do work. If you just connect two heat sources together, ultimately those two heat sources, or heat source and heat sink, a source and a sink of energy, will ultimately generally come into some kind of an equilibrium. It's called thermal equilibrium state, where the energy transfer from one place is equal to the energy transfer from another place. And so Earth-Sun system is actually an example of this balance. Ultimately, Earth receives solar energy from the sun, and then it also radiates that energy, and the temperature of the Earth ultimately settles at a point where the balance of energy back and forth are equal. So the amount of energy received is equal to the amount of energy released. So that sort of sets the typical temperature here. And of course, the typical temperature actually depends on the conditions. So the amount of energy we radiate, the Earth radiate, depends on the transparency of the atmosphere. So the actual temperature we sit at depends on the conditions here. But over a course of, say, 100 years, if there are no changes in those conditions, the temperatures would settle and there would be equal balance, and the temperature would be constant. Now, over the last 100 years, we have changed those conditions. So if we change those conditions, then the temperature may change on a shorter time scales. And that's an example of global warming. And so that we'll discuss in 10 weeks or so, or actually Rich Moller hopefully will come and talk about that. So the point is that if you don't change conditions, ultimately we reach equilibrium and temperature stays constant. If you change conditions, you may either increase local temperature or decrease it. Yes?
When the book was talking about power, it referred to it as kilowatts instead of kilowatts hour. Are we supposed to assume that they're per hour?
Okay, so the question was, the book talks about power and talks about units of kilowatts instead of kilowatt hours. Great question. I'll jump right into it in about 10 minutes. So the questions of how we measure energy versus power, what the difference is actually the topic for today. So let me defer that. Do you guys have any other questions? Yeah, I'm sorry to defer some of the questions about the book because, well, the point of me being here today is to hopefully explain some of these concepts in greater detail. And if it's unclear as I talk, please ask. Any other questions so far? Okay, so let me first give you a reminder about the organization of the class. Let me change this to my screen. The course is on B courses. There's so this is the B course page. Actually, I have here a page where I'm supposed to register my clicker. So let me remind you of two things. First of all, most of the communication, all of the homework assignments will be on B courses. In fact, the first two homework assignments are already posted. One of them is available for you to actually enter and answer. And the second homework we've uploaded but haven't activated yet. So if you go to the home page here, which, okay, I shut off my internet deliberately so that it doesn't distract me. If you go to the home page, on the bottom of the, and scroll down, on the bottom of the page is a calendar. Is the set of reminders of what's coming up. The first homework is coming up on Monday. It's an essay that you're supposed to write. And the second part of the homework is on Tuesday of next week before class at 9:30. Would be a 5-question multiple choice quiz. So don't forget, first part. Second part is we talked about clickers. Last time, I will start using them next week as a first test of the technology, and then we'll actually start using them for real with the 2 to 5% extra credit bonus for you using clickers next, well, in 2 weeks from now. So, my apologies. Clickers come in 3 flavors. And somebody did ask, what kind of clicker should I buy or should I borrow? Clickers come in 3 flavors. These are iClickers. Number 1, number 2, and something called iClicker Go, which is the Android or Apple app, or you can even do this on a laptop. So I've activated all 3. So I'll bring my wireless unit next week. It can be used with either clicker type 1, an old style, which only lets you answer A, B, C, D questions, or clicker type number 2, which is alphanumeric. We'll only use simple A, B, C, D questions, so either clicker would be fine in this class. If you like to subscribe to this modern app technology, you're welcome to also. To be quite honest, I have never used the apps, so I don't know how reliable they are. I'm told they are, and we'll test this next week. Any other questions about logistics? All right, so let's, if not, let me jump right back into the questions at hand as we talked about energy. I think probably if I wanted to summarize what energy is in basically 1 or 2 words, I would say the following. Energy is sort of physicist's universal currency, or physics' universal currency. I have to be a little careful. Energy can be traded. Energy can be converted. Unlike universal currency, well, unlike dollars, for example, which are no longer backed by gold, I understand, but rather backed by the honest word of Uncle Sam, total amount of energy in the universe is conserved. The entire amount of energy in the universe, we believe, is constant. And so most of the physical processes involve not creation of energy from nothing, but rather transformations of one type of energy into another. So mechanical motion is one example of a type of energy. In other words, mechanical motion requires you to, in order to initiate mechanical motion, requires you to spend energy. The motion itself can be characterized by a concept of kinetic energy. Moving bodies contain in themselves a certain amount of energy. This is called kinetic energy. There are 3 types. There was a question here. There are 3 types of energy that we know. Kinetic energy, which is really a characteristic of the motion. You can write down the formula, or you can just remember the concept that the amount of energy contained in the motion of a body depends on 2 things. It depends on how massive the object is. This, again, you know conceptually. In order for me to move in a relatively light object, I need to spend less energy than to move a heavy object. The opposite is true. A huge asteroid, like we watched the clip from Armageddon last time, a huge asteroid of the size of this building, or of the size of, say, 1/4 of this building, can produce, moving at high velocity, 30 kilometers a second, can produce an impact equivalent to a nuclear explosion. Contains a lot of energy in it. A single atom moving at the same velocity will be barely noticed. You are now continuously bombarded, by the way, by cosmic rays. We are sitting here, and every minute, a cosmic ray muon passes through the tip of your finger. Actually, slightly better demonstration, or slightly better analogy is that the tip of your finger has an area of roughly 1 square centimeter. Your pupil in your eye has an area of roughly 1 square centimeter. So if you go out into the Memorial Glade in a nice summer day, spring day in a few months, lie down, every minute something will hit you in the eye. It's a cosmic ray muon. They're extremely light, and so you don't notice. I assume that if a meteor of the size of this building were to hit you in the eye, you'll actually feel it. So the amount of kinetic energy depends on this mass. It also depends on the velocity. It depends on how fast an object is moving. This you actually have learned, hopefully, when you're 15, 16, when you took driver's ed, right? You're told the amount of braking distance increases with speed. If you're driving at 30 miles an hour, it takes a certain distance to stop. If you drive 60 miles an hour, it takes 4 times the distance to stop. I'll explain you in a second why the stopping distance depends on velocity. It has to do with the concept of work. But the primary reason is that it takes, if you're moving at twice the speed, you have 4 times the energy. And so you need 4 times more action of some kind, called work, 4 times the distance to stop you, to convert all that energy into heat, to waste all that energy. So this is kinetic. And the second part is called potential. So potential energy is just what the word says. One way to describe it is potential energy tells you about potential to produce motion. It describes the potential to move things. And so typically, an energy, potential energy has to do with forces, has to do with interactions. We'll discuss forces and interaction in 2 weeks. But here's an example. I have a spring here. If I extend the spring will not move yet. If I just extend it and hold it in place. This mass on the bottom here is not moving yet. But the spring, I had to apply a force in order to extend the spring, and the spring now has a potential to produce motion of this mass. It has stored potential energy. If I were to release this mass, it will start moving. And this motion, up and down, can be quite destructive, is an example of energy transformation. It's a continuous transformation of potential into kinetic, and then at some point the mass stops. At that point it also has a lot of potential energy, but not kinetic yet. So this bobbing back and forth is an example of continuous transformation of potential energy into kinetic, kinetic into potential. Motion of this pendulum is another example. We'll talk about this. Whoa. Why did James put this thing there? Oh, I know. It's a protection for a volunteer. So this bowling ball motion is again another example of conversion of potential to kinetic. If I take this bowling ball and I move it to the side a little bit, in order to move it, I have to apply force. I have to spend my carefully earned chemical energy that I have. Haven't eaten breakfast today. But at this point in time, the ball is not moving. It doesn't have any kinetic energy until I release it and produce motion. So that's potential. And then there's actually a third part which you don't, in fact, notice most of the time. But all of you, independently of whether you've eaten today, if you're actually even independently of whether a body is alive or dead, any massive body, human body, physical body, contains a lot of energy in it, and that's Einstein described by the famous equation that you see on T-shirts called E equals mc squared. What it actually says is that there's a third type of energy that exists simply because matter exists. We usually don't notice it. We usually don't notice it because in most everyday life, we don't actually transform matter of one kind into matter of another kind. I take this ball and I move it here. The whole process of motion transforms energy from potential to kinetic, but the mass of the ball doesn't change. And so we don't notice that additional energy source. But if you were to find a process that can change a mass of an object, you have potential to either release some of that stored energy, or if you're creating new massive object, you have to spend the corresponding amount of energy. And so this is usually most important when you deal with elementary particles annihilation, but actually every chemical process can be viewed from the same point of view as well. Whenever you burn gasoline, you're actually changing the mass of the substance a little bit. Someone could actually describe this process as not releasing chemical energy stored in the bonds of electrons and nuclei in carbon and hydrogen, but it can be described as a change of the mass of the combination of gasoline and oxygen and the release of that mass energy. So the two descriptions are in fact kind of philosophically and fundamentally equivalent. I'll get back to that in just a little bit in this energy source and how to tap into it, but we'll describe it in much greater detail towards the end of the course when we actually talk about cosmology, particle physics, and all the interesting things that I deal with on almost everyday life. Well, in my other everyday life. But actually the other way of looking at it is that the universe itself has a mass, and so in some sense the total amount of energy stored in the universe can just be associated with that mass, or the other way around, the mass of the universe can be associated with the energy stored through this equation. So if you know the mass of the universe, which we do, at least the mass of the visible universe, you can compute the total amount of energy. And that energy is vast. And this energy is vast because this little coefficient. If you compare this equation to that equation, there's a velocity squared here, there's a velocity here, the speed of light is a huge number. Our typical everyday speeds, if you move as a human at velocity of sort of meter a second, 3 feet a second, if you're an Olympic runner, you say Bolt runs at 100 meters in 9 seconds or so, 9 point something. So 10 meters a second velocity. Speed of light is 3 times 10 to the 8 meters a second, so 3 with 8 zeros to it. It's a significantly large number, and so that's why the amount of energy stored in the motion of light or stored in the mass itself is huge. We'll get back to that. So now the question about energy conservation. So I said that energy is sort of the kind of like a currency that can be traded, that can be exchanged, or can be converted from one type to another. It doesn't disappear or reappear anywhere. It can be stored, typically in some kind of a potential energy. Here I move the mass and I stored the energy temporarily before releasing it. Energy can be stored in electrical form, like in these capacitors. Energy can be stored in gravitational field by moving objects up and down. And then it can be converted from potential kinetic, from chemical to thermal, etc. But the total amount is conserved. And that actually maybe is a good thing in some situations. In other words, energy doesn't just appear out of nowhere. And if it disappears visibly, the disappearance typically is a conversion of mechanical energy into heat, or some kind of a conversion of one type to another. Let me demonstrate this concept. For this, I will need a volunteer, somebody relatively brave. Yeah, come on down. So, what's your name? Casey. Nice to meet you, Casey. So this is a demonstration of conservation of energy, and in fact, the fact that the universe does not behave like Federal Bank, it doesn't print money. No, it doesn't, produce energy out of nowhere. So I have this bowling ball here. Why don't you stay over here on this side? And whatever you do, I'll come in a little bit closer. Whatever you do, don't lean forward. have this bowling ball. I'll move the bowling ball close to the chin, Casey's chin, and I'll let it go. And we'll observe a transformation in energy, and we hope, for Casey's sake, that energy doesn't appear out of nowhere and the ball doesn't sort of jump higher than it was when it started the process. Physics is experimental science. Ready? Go. So we observe transformation kinetic potential, the ball comes back. Luckily, energy doesn't appear out of nowhere. Federal Reserve hasn't printed enough joules yet. The process will repeat itself over and over again. Thank you, Casey. Thank you. Let's give her a hand. You did notice, however, that the ball, in fact, came back not quite to the same height, luckily for Casey. It clearly didn't jump higher. It came back a little bit lower. Why did it come back a little bit lower? I started with some energy that can be associated with the elevation of the ball. After one cycle, the elevation was smaller. After 2 cycles, it was smaller still. After 3 cycles, it was smaller still. Now this ball is only coming back sort of here somewhere. This is an example of, again, transformation of energy from a purely mechanical, absorbable, into something else that is much harder to see visually, transformation of it into heat. This ball is suspended up in the ceiling somewhere. That suspension point produces friction. The cable grinds against some hook, and this is an example of a waste of mechanical energy or transformation it into small increase of temperature of that hook. The ball also has some friction against the air, and that wastes, robs it of its mechanical energy too, or rather transforms that mechanical energy into mechanical energy of air molecules. So these are examples of transformation of mechanical energy into heat, or rather the losses of most of the mechanical energy to friction. And that's one of the reasons why you haven't heard about discoveries of perpetual motion. In fact, in the 19th century, I think it was a French or British, now I'm forgetting, French, I think, Academy of Science, had a contest. They would pay good money by the time to any inventor of perpetuus mobile, a perpetual motion machine. There were many claims. None of them came true. In order to have constant, perpetual, literally infinite motion, you have to have a device that loses no energy. And that's physically impossible for anything that has any physical contact with any environment. And we always have contact with the environment. Even if you don't touch an object, you still are connected to the environment by radiation, by transfer of energy through electromagnetic waves that we'll discuss next week. So any process, any mechanical motion always transforms energy into heat, and that's the subject of the third law of thermodynamics, that ultimately all mechanical energy gets transferred into randomized motion of molecules, and therefore causes increase in randomness. That's known as entropy. Now, every day, of course, we deal with more mundane sources. We have chemical energy if you burn a fuel, or if you burn calories that we eat. Those processes involve transformation of atoms, or rather transformation of molecules. We take, let's say, a molecule of hydrogen, we combine it with a molecule of oxygen that produces water and releases energy, typically in the form of heat, typically in the form of motion of this water molecule that we then can capture and convert into electricity. When we burn gasoline, gasoline is hydrocarbon. Carbohydrates is what you eat, hydrocarbons is what you burn. It's a molecule that has also a lot of hydrogen in it. also has carbon. Burning gasoline produces water and produces carbon dioxide. This chemical process releases energy that then can be converted into a more useful form, from heat into mechanical motion, electrical motion, etc. So this is one example. So what actually happens in practice is very similar to what happens with the spring. Chemical energy really is a transformation of potential energy stored in the attractive force between an electron and a nucleus on an orbit of one of these atoms into vibrations, into motion of those atoms, and then we can convert those vibrations we associate with heat, convert those vibrations to more useful mechanical energy of macroscopic objects. So chemical energy is another example of conversion of potential into kinetic. Nuclear energy works exactly the same way. Nuclear energy is an energy associated with the attraction between protons and neutrons in the atomic nuclei. Atomic nucleus is much smaller than an atom. The four attractive forces are much stronger than the attractive force between an electron and nucleus. And so the amount of potential energy stored in a nucleus is significantly larger, the amount of potential energy stored between the attraction of electron and an atom. And that's one of the reasons why releasing nuclear energy, single act of, let's say, nuclear decay, uranium nucleus, releases about 1 million times more energy than a single act of burning uranium and converting it to uranium oxide, or a single process of burning hydrogen and converting it into hydrogen dioxide. Nuclear fusion is another nuclear process where you can combine two independent atoms, for example, two hydrogens, into a nucleus of deuterium, heavy hydrogen, and that releases some of the potential energy stored in those nuclei in the form of heat, in the form of kinetic energy, motion of those nuclei, an amount of energy just by the fact that those nuclear forces are much stronger than electrical attraction between atoms. The amount of energy released in a single nuclear process is about 1 million times larger. That's one of the reasons nuclear power is relatively, can produce per gram of material significantly more energy than chemical. We know about electrical energy. These are examples. I push the laser pointer and something happens. Electrical current flows, and that electrical current can be converted into kinetic energy of moving photons that you can observe. Electrical energy is the kinetic energy of moving charges, moving electrons in a wire, or sometimes moving ions in plasmas or in semiconductor devices. We know solar energy. Solar energy is, again, motion. Solar energy is the kinetic energy of moving photons. Photons travel through space from the sun to us or from the tip of the laser pointer to the wall, and that motion contains energy in it. It's simple kinetic energy of just the particles that you don't observe or cannot really touch. You can observe them, but they're microscopic rather than macroscopic. And then, of course, wind, hydro, energy, etc., is again an example of kinetic energy of moving macroscopic objects, air for wind, water for hydro. And so we'll discuss all of this in great detail, but now let me come to units, and there was a question about that. Again, physics is a quantitative science, and so we need to talk about units, or rather energy in some numerical form, but also energy being the universal currency, we want to quantify the currency, and we typically want to quantify the energy as well. So physicists measure energy in this unit called joule. Joule was a British scientist who studied heat. So, most physics units are named after famous physicists. Newton's, for example, described forces. Joule described energy. Watt, James Watt, was another British physicist, scientist, that describes power. Joule is a unit, if you take a unit of force, interestingly enough, a unit of energy is related to forces and distance. We'll get back to that in a second. And so in this country, we measure forces in pounds. This is actually something that some people don't realize. Here, typically, when you go to a store and you buy a pound of, I don't know, meat, right? You think that you're buying a massive object, so you associate pounds with the mass. It actually, pound is in fact a unit of weight. And so, you know, if you buy a pound of meat here on Earth, or if you buy equivalent amount of meat, say, on the moon, you'll get slightly less than a pound on the moon, or 7 times less than a pound. You get a smaller weight, but the same mass. Pound is a unit of force. And then force multiplied by a foot gives us a units of energy, joules. And so I'll show you an example of calculation of how to compute the amount of energy you produce or you spend doing some kind of physical activity. And so the typical conversion is that 1 foot-pound is roughly 1 joule, 1.5 joule. In chemistry or in food science or just for nutritional purposes, we talk in this country again about calories, units of calories. And this is actually a place where you have to be a little bit careful about. Calories are very strange units for 2 reasons. Historically, they were defined as the amount of energy. 1 calorie is the amount of energy required in order to heat up a gram of water by 1 degree centigrade. That's a formal definition. But you have to pay attention to how calorie is spelled. 1 calorie with a little c is 4 joules. But if you look at nutritional information on foods you eat, depending on which country you bought them in. Do I have any foods? Oh, here's Worker shortbread cookies, quite nice. If I look in the back, this one apparently was made in Scotland, and nutritional information is written in kilocalories. Kilo is a unit that means 1,000. So 1 kilocalorie is 1,000 calories with a little c. In this country, spelled with a c in the capital case. So 1 calorie with a capital C is the same as 1 kilocalorie in Europe. And that's a unit equivalent to about 4 kilojoules, 4,000 joules. Typical human over the course of the day consumes anywhere between 2 to, well, depends on the human, 2 to 10,000 calories. 10,000 calories is the diet of Michael Phelps when he was training for Olympics. That's a large amount of food. Typical male, I think, consumes about 2,500 calories a day. Typical female, about 2,000, but of course, there's a great range. So a calorie is a kind of a humanly absorbable unit. If you drink a bottle of Coke, you consume, about 300 calories. This shortbread cookie is about 50 calories. So, calories are meaningful amounts. If you are living at home and you're paying for electricity, you typically get a bill, and that bill describes units of energy. You pay about 13 cents per kilowatt hour if you live at home. So another units of energy is associated with spending electricity, and here is you have to be careful. The unit of energy is kilowatt hour, which is equivalent to 4 million joules, or about 1,000 calories. There's another unit if you're buying an air conditioner. Then the air conditioners are typically rated in how much energy they can remove from your house per unit time. So typically, air conditioners are rated in BTUs per hour. So BTU is British Thermal Unit, is a unit of energy, and it's roughly equivalent to kilojoules. Now, fundamentally, in quantum physics, we deal with energies in very different units. we deal with energies called electron volts. We deal with microscopic objects. Each of those microscopic objects contain very little energy. For example, this chemical reaction of burning oxygen and hydrogen producing water typically releases about roughly an electron volt, about 1 electron volt per a single chemical reaction. And of course, so in order to obtain a large quantities of energy, you need to burn a lot of single atoms. So the fact that there's a lot of atoms in a liter of water and a liter of gasoline, about 10 to the 24 atoms in a liter of fuel, so means that a lot of energy can be released as a sum of very small, a very large amount of small microscopic steps. So typical energy of a single object of light, a single photon, is about 2 to 3 electron volts. But summed over a large number of photons can produce a significant amount of visible energy. Let me actually demonstrate that. I said that the photons carry kinetic energy, and that kinetic energy can be transferred into heat, can be converted into electricity, but can also be observed visually, mechanically. Kinetic, light carries with it energy. We can actually quantify it by a device called, okay, I'm spacing out for a sec. We have a device here that measures the amount of light absorbed by dark and light panels. It's called radiometer. I'm getting senile in my young age. This is a device called radiometer, measures the amount of radiation, amount of light absorbed or carried or absorbed by this object carried by light. The way it works is the following. It's a bulb filled with a small amount of gas. You can see the little petals on the radiometer rotate, and one side is painted white, the other side is painted dark. As you know, dark clothes absorb more sunlight, light clothes reflect more sunlight. So the darker side will typically absorb more energy from the light. The brighter side will absorb less energy. There will be a difference on the two sides. The difference produces air currents, and the amount of air current and the air currents will move the radiometer. Ultimately, this is an example of conversion of kinetic energy of light into mechanical energy in the spinning of the radiometer. There's an intermediate step, which is conversion of that into heat. And so even though a single photon carries minuscule amounts of energy, a stream of photons can carry enough energy to produce visible mechanical motion in this radiometer. So again, light obviously contains energy. Now, we'll get back to why units of electricity are called watts in just a second. Can you switch back to the screen? Thanks. So when we talk about energy sources, again, we can talk about kilojoules or calories. It's useful to quantify fuels that you burn or sources of energy that you spend in some units, quantifiable units that are useful for large-scale economies or useful on human scales. This may help you answer the question is what fuel is best. So here, I think a similar table also is in the book with the slight variations. Here are the comparisons of different types of energy sources, or typical types of energies that can be stored in either potential or kinetic form. For example, weapons are typically explosives are typically quantified in their energy release equivalent to a kilogram or gram or a ton of TNT. That's a conventional explosives. If you build a nuclear weapon, the yield, energy release of a nuclear weapon will be quantified in megatons, and megatons not of uranium, or megatons of TNT. So typically in the energy release equivalent to some mass of a conventional weapon. TNT is actually, as an energy source, isn't that great. TNT explodes by converting chemical energy in a, it's a trinitro something, I forget. So chemical bonds in that molecule in nitrogen and carbons can be converted into heat very quickly, but in a per-gram of that substance, only about 3 kilojoules or a kilocalorie, or calorie with a capital C, is released. That's about almost 10 times, or rather, 8 times smaller, the amount of energy you get by absorbing a gram of chocolate, or rather a gram of chocolate chip cookie. So does it mean that chocolate chips can be used by terrorists as explosives? Thankfully, the answer is no. Well, they can be used to defeat it in some other ways. You know, after eating a lot of chocolate chip cookies, you don't move very fast. So the amount of energy released, 5 calories per gram is a very significant amount, but that energy is released slowly. So there's a difference when we discuss, the total amount of energy tells you about the total amount of this currency that can be traded, but the rate with which you spend it is also important, and we'll talk about power in a second. Gasoline is actually a significantly better energy source than TNT. There's a reason we don't drive on TNT. Well, first of all, there's more energy per gram on gasoline. Secondly, we can make it to burn slowly rather than very quickly. Gasoline is a fairly good energy source, about twice better than chocolate chip cookies. So that's why we don't drive on chocolate. Hydrogen is even better per gram. Uranium is significantly more energetic per gram of the material. And this difference is between uranium and, let's say, hydrogen of roughly 6 orders of magnitude per gram, is the difference due to the physical process that goes on when you transform these energy sources from one type to another. As I told you, burning gasoline, digesting cookies, blowing up TNT are examples of chemical transformation. And in the process of chemical transformation, we release energy stored in the attraction of electrons to atoms. That attraction is about 1,000,000 times weaker than attraction of protons and neutrons in the nucleus. So if you're able to capture, or rather transform, that potential energy stored in the nucleus, you can release, for a single process, 1,000,000 times more energy. So per gram of material, uranium-235, which is the fuel fueling nuclear power plants, most nuclear power plants, non-weaponized power plants, and uranium-type bombs, the process of nuclear fission, releases 1,000,000 times more energy. If you take the same hydrogen that you would burn, not the hydrogen molecule, if you just burn hydrogen combined with oxygen, you release 100 kilojoules per gram. But if you take the same hydrogen nucleus in the hydrogen molecule, there are 2 hydrogen nuclei there in a single molecule, if you were to fuse them together, or if instead of the regular hydrogen you take heavy hydrogen called deuterium, or even heavier hydrogen called tritium, that contains, instead of a single proton, deuterium has a proton and neutron in it, tritium has proton, 2 neutrons in it. It's a heavier cousin of the standard hydrogen. If you take that nucleus and fuse it together with another nucleus, in this reaction called deuterium-tritium fusion, take one nucleus of hydrogen take another nucleus of hydrogen, put them together, producing a nucleus of helium here, making not just a chemical, but actually nuclear transformation. That process releases a very large, vast amounts of energy, about 5 times more than the corresponding decay of uranium nucleus per gram. So fusion, that's one of the reasons there's a great amount of research into fusion energy. But there's also the reason why you haven't heard of fusion power plants yet. Technologically, harvesting that energy is very difficult. Again, we'll discuss technological aspects of fusion energy as well as fission in 3 or 4 weeks. So if we were to able to capture this amount of energy and convert it into electricity at 100% efficiency, there could be large amounts produced. But this technology doesn't exist yet. And then finally, if you have a gram of matter and a gram of antimatter, and you were to combine them together, as I told you a few minutes ago, the amount of energy stored in the mass of any substance is vast, is in fact the amount of energy produced by annihilating matter and antimatter together of gram of that material is roughly 10 to 11, 1 with 11 zeros, kilojoules. 400 million is 4 with 8 millions, and this the 11 million, there's a factor of 1,000 there. So the amount of energy stored in the mass is even greater, is the largest amount of energy you can ever possibly release. Now, there's also a reason why you haven't heard about antimatter power plants. The main reason is that there's no antimatter around. So in addition to knowing how much energy is released, so if I wanted to ask you, what's the best energy source? What would you tell me? I mean, what do you think? Maybe uranium is the best energy source. Well, it gives you a lot of energy. Do you know what the most common source for producing, what the most common fuel for producing electricity is? Coal. Why is that? It's cheap. It's dirt cheap. And there's also a lot of it. So, if you were to ask, what's the best energy source, the answer is, it depends. It depends on not just the amount of energy per gram, but also depends on how much energy is required to produce that gram. Where is it? How much energy is required in order to build a power plant that would harvest that energy that we can release in burning or fuel or decays of nuclear material. And not the least important aspect is how much waste such power plant produces, both chemical waste, nuclear waste, or thermal waste. And the last part we'll discuss when we talk about global warming. So costs are important. This actually is an interesting table to look at. You may be surprised, in fact, at some of these aspects. For example, we typically, again, if you open up your electricity bill, you will find numbers on the electrical bill in kilowatt hours. If you also pay for natural gas, typically you'll find on the bill something called terms, or in Europe maybe you'll find BTUs. But kilowatt hour is a convenient unit to describe. It's equivalent to boiling water in an electrical kettle for an hour. Typical power you spend in the electrical kettle, in a rice cooker, or in an electrical iron is about a kilowatt. So boil water for an hour, you spend a kilowatt hour. That will cost you 13 cents. It's not that much. By comparison, if you get that electricity from a car battery or another equivalent source, you'll spend a little bit more, roughly twice as much. But if you actually look at how much does it cost to produce this electricity at a plant, if you're using a coal thermal power plant, that power plant would have spent about half a cent per kilowatt hour. So PG&E charges you 13. They spent on fuel only half, but of course they also spent a lot on building plants. They spent a lot on transmitting electricity from the plant to you, their taxes and other such things. Few people realize that nuclear power is also dirt cheap. Now, there's a little asterisk here. Now, one could also think that the solar power is free. After all, sun shines independently of whether we harness that energy or not. Of course, when you compute the amount of the cost per kilowatt, it's highly subjective. What does it, how much does it cost to produce kilowatt of electricity using coal? Well, what do you need to do? You need to mine the fuel. You need to build the plant. You need to pay the workers who work at the plant. And then eventually there may be hidden costs that you don't realize, which is dealing with pollution and waste that it produces. So this table is a little bit subjective. This price, this cost for everything up to here is actually just the cost of fuel. In comparison, so for thermal power plants, this cost actually dominates. If we discount the cost of dealing with issues of global warming, for example, pollution, if we discount that, which is a subjective thing to do, the cost of fuel dominates. And so, indeed, coal is A, dirt cheap, B, very abundant. The amount of coal in the world will last us hundreds of years at the current consumption levels. About, when I was in school, more than 20 years ago, probably before you were born, you remember things, or you can read in history books about energy crisis of the 80s. The OPEC, the organization that controls the production and distribution of oil, instituted embargoes. At the time, in the early 80s, it was believed that the amount of oil, the actual that's converted to gasoline, jet fuel, etc., would last us, 30, 40 years or so. So now we don't believe that to be the case. New energy sources, for example, shale, natural gas, and equivalent amount of oil are being discovered. It takes a little bit more to mine. It's more expensive to mine. And so the overall cost, but the amount is still will probably last us about 100 years or so. The cost of producing that gasoline is 20 times more expensive than the cost of producing coal. Of course, gasoline is more convenient to operate portable, movable objects with. So when you're considering an energy source, you have to consider not just the economy and the cost, but also how you would use that source. If you're building a car, it's more effective, it's more efficient to build a small engine that burns the amount of gasoline. It's more convenient to store fuel in liquid form. You just put it in a tank. It's more convenient to distribute fuel in liquid form. Yeah.
I'm confused about the difference between the numbers of the first column.
Okay, so and then you can see the two columns. Different types of fuels are used differently, right? If you move in the car, unless you're buying a Chevy Volt. Chevy Volt is an example of a hybrid car with a gasoline engine, but that gasoline engine is not connected to your drive shaft directly. That gasoline engine is a little power plant that churns there when you need it, produces electricity, and the motor is actually electric. Toyota Prius doesn't work that way. Toyota Prius actually has two engines, electric engine and a gasoline engine, and gasoline engine kicks in when you need more power. So if you use the fuel to produce mechanical motion directly, and if you want to spend the kilowatt hour equivalent energy units, it costs this much. converting fuel to electricity is a wasteful process, in a sense that it's not very efficient. You notice that there's a difference of roughly factor of 3 between this. What it means is that the efficiency of producing electricity from conventional fuels, from burning coal, burning gas, or burning either coal, natural gas, or oil, the efficiency of thermal engines is about 30%, which means that if you burn a kilowatt hour worth of gas to convert it to that energy to electricity, you will only use 30% of that energy, and the other 70% will be released into atmosphere as heat. It's not a very efficient process. So if you actually want electricity, you need to pay that factor of 3 in additional price. Of course, if you start with electricity directly, the cost is the same. So PG&E sells you electricity at 13 cents per kilowatt hour, and you get it as electricity. You don't need to convert it anymore into any other forms. They spend typically a few cents per kilowatt hour, depending on the type of the energy used. Solar and nuclear are actually, these costs are mainly fuel costs. These costs are actually not fuel costs at all. I told you that the nuclear power produces 1 million times more energy per gram. So if you want to produce a kilowatt hour of electricity using a nuclear power plant, you don't need that much fuel. In fact, nuclear power plants get loaded roughly once a year. You load several tons of uranium in the fuel cells, and you let it cook there for a year, and then you pull out fuel rods and replace it with a fresh one. Yeah?
Why exactly is electricity so useful? How do we convert from thermal to electrical?
Why is the electricity why is the electricity that useful if you lose factor of 3 in energy conversion? Well, how do our devices operate? Yes, most of the devices that we use in our everyday life now, in the 20th and 21st century, work on electricity. So, you can, put a little gas tank next to a laptop, fill it up every morning. It's not that convenient. Here's an here's the thermal engine. This is a it takes a while for it to cook and get going, but you wouldn't imagine having this thing next to your laptop. You wouldn't be able to hear me if each one of you would have this little motor chugging along. So most of our progress in the last century was achieved because we learned how to harness the power of electrical motion. All of these devices work on electricity. Electricity is very useful to us, and therefore we want the service provided by an electrical company rather than just necessarily the gas company. But yeah, you do have to pay a factor of 3 in the energy penalty. So now let me go back to the table. If you are using nuclear power, most of the cost is not in the fuel. If you're using solar power, most of the cost is not in the fuel either. There isn't any fuel. You're harvesting the energy of the sun. Most of the cost is in producing equipment necessary to harness that power. The nuclear costs are roughly cent per kilowatt hour, would include the cost of building the power plant, getting permits, operating that power plant, and then 20, 30 years later, dismantling it and cleaning up. Most of the cost of solar power amortized over the lifespan of about 20 years or so is in building solar cells, installing them on your roof, or building solar cells and putting them in the Mojave Desert somewhere. So let me come back to that point, and I'll give you a few numbers in a second. Let me first address the question that was raised earlier. I said half an hour. I talk a little too much. There's a big difference when we discuss energy and power. There's a conceptual difference between the two things, between the two concepts. Power measures the rate of energy consumption or energy production. So in other words, power is a measure of how quickly you produce energy or how quickly you spend energy. Power is sort of equivalent to speed. If I want to move from here to there, I can do it very fast. Or I can do it excruciatingly slowly. I can cover the same distance, ultimately, if I have enough patience. How fast I do that depends on my speed. If I want to boil a kilogram of a liter, quarter of a gallon, a quart of water, I need to spend a certain amount of energy. I can do it slowly by taking that quart of water and moving to the hot desert and just waiting, or putting it in the sun and hoping that eventually it will boil. In fact, it will not boil, it will evaporate. The amount of energy spent over the next day will be equivalent to putting the same quart on the stove, turning the heater on, letting the water boil, and then waiting for all of it to evaporate. The amount of energy spent is exactly the same. The amount of time that it takes for the same process may be different. And it will be different because the amount of power delivered by a gasoline heater would be higher in that particular instance than the amount of power I would collect from the solar power. So power is the rate with which the energy is either released or the energy is consumed. And here's where the different power sources also, different fuel sources also can manifest the differences. Explosives release power very quickly, whereas if you operate an engine, you want to release this maybe equivalent amount of power, but more slowly. So food consumption, gasoline burning in an engine is a slow process, explosives are a fast process. Amount of total energy released may be the same. The time over which it's released will be different, and therefore the power produced will be very different. We measure power in the units of watts after James Watt. Ironically enough, James Watt was most famous for introducing a power unit of horsepower. And despite the fact that he produced or he measured the amount of power output of a horse, he had some big horses move water around up and down from some wells, and he measured the amount of power released by a typical horse at the time in Britain. This was the unit of power. One horsepower is equivalent to roughly 1 kilowatt. So if you have a horse and she's going around a circle somewhere, moving water around, she's producing a kilowatt, she does it for an hour, and you have enough power, or you have energy to operate your rice cooker for an hour. The amount of power spent by your rice cooker, which incidentally you're not allowed to use in the dorms for some reason. Why rice cookers are not, I don't know, boilers, boiler plates. I think you are not allowed, boiler plates either, right? Dangers of fire hazards, I assume. So the typical boiler plate uses about a kilowatt of power. You operate it for an hour, and you've just spent kilowatt hour of energy that costs you 13 cents. You can produce that by having a horse work for about an hour. So horses are not very efficient sources of energy. Well, not very efficient, not very abundant sources of energy. Humans actually often as powerful or more powerful than horses. There's so horsepower unit is a kilowatt, and the BTU per hour can also be used as a unit of power. Let me give you another reminder of energy. So I said that a joule is roughly pound-foot. Horsepower is a kilowatt, so watt is 1 joule per second. So I can basically say the following. I can sort of compare units, and I can say that 1 pound foot per second is roughly 1.5 joules per second and 1.5 watts. So I can use either this unit or this unit. This unit, pound per foot, is a useful unit to measure human power output. It works in the following way. Pound is a measure of weight. Foot is a measure of distance. What does this mean? It means that if I take an object that weighs a pound and I raise it by a foot, I have just spent a pound-foot of energy, which is 1.5 joules. If I do it in a second, I produced a watt, 1.5 watt. So let me use this knowledge to actually measure the power output of a typical human. I'll claim I'm a typical human. I do actually need a volunteer. Somebody needs to hold a stick. Come on down. Actually, while I'm doing that, let me ask you a question. Are there any, buff people around? Do you guys bench press? I mean, I'm sure some of you do. You guys bench press? How much do you guys, how much do you bench press? 300 pounds? 4? 2? I mean, I don't, so, don't ask me. 370, let's call it 400 pounds. So you're a much better human than I am, in that sense. So how do I compute? So we'll, compute your power output. You have 400 pounds, something to strive for. Your arm length is bigger than mine. Let's call it 3 feet. Your arm is sort of this big, right? Maybe a little shorter. We'll round it up. 3 feet. So this amount of energy you use in a single lift. You lay on your back, right? You bench press like this. Okay, my arm is not quite. My arm is 2 feet long. Yours are longer. What is it? 1,200 pounds feet. Let's convert into joules because that's, I remember better, multiplied by 1.5. Let's call it 2,000 joules, roughly speaking. How long does it take you to bench press? Well, it depends. Let's call it half a second if you do it really a fast jerk. Amount of power is 2,000 joules divided by half a second is 4,000 watts. That's actually about 8 horsepower. You're pretty good. So a human can be as good as 8 horses, well, 6 horses, right? 4,000 watts is approximately 6 horsepower. Let's do it for me. I can do the same thing. I can measure my power output. I'm not very strong. But I play hockey, so my feet are better. I hope to be a little bit more impressive. I can measure how much I elevate myself. We'll start with my, most of my mass is in my gut. So I start sort of here. And then when I jump, your job is to see where I elevate sort of my gut. Roughly. Ready? Go. Oh, he's very complimentary to me. Thanks. So, sort of this much, 3 feet. Okay? Thank you. So what's my power output in this process? Same calculation applies. You have to know how much I weigh. I'll tell you a dirty secret. So my power output is, I jumped 3 feet. I weigh, I'll lie, 160 pounds. Multiply that together, that's 480, call it 500. Pound-feet, 750 joules. And how quickly do I jump? I call it half a second too. half a second, half a second, 1,500 watts is roughly 2 horsepower. So, you know, I'm as good as 2 horses. You guys are as good as 6 to 8 horses. Human peak power production can be very significant. Of course, none of us sustain this amount of power continuously, right? I cannot keep jumping for an hour. So I cannot produce kilowatt hours very easily. I'll slow down eventually. These guys are better. So, you know, humans, despite what you've seen in the matrix, humans are actually not that so abundant energy sources. Although we do spend a lot. We eat, oh, you guys probably consume 5 kilocalories, 5,000 calories a day, 4 to 5. If I watch my intake, I will probably spend 2,500 calories a day. These are significant amounts. That's equivalent to a typical power output of about 10 kilowatts, if you sort of put the numbers together. So humans actually burn about 10 kilowatts in real time. But of course, you know, we use it primarily for just our normal motion. And for motion of liquids and breathing and things like that. So these are the typical macroscopic units of power and energy. And did it answer the question about the difference between watts and joules?
Like watt the same as a watt hour.
And watt is not the same as the watt hour. So again, the difference, so if I look at the units of, oops, my bad. If I look at the units of energy, energy is measured in kilowatt or watt hour. So that's the amount of energy. If I, as a human, produce a kilowatt continuously for an hour, I will spend an energy of kilowatt hour. That's a unit of energy. Kilowatt itself is a unit of power. It gives me a rate. So if I keep lifting, I will producing an hour, multiplied by how long I lift, it will give me energy. So kilowatt hour is a product of power and time. I produce a certain amount of power, like kilowatt, multiplied by an hour gives me kilowatt hour, unit of energy. Kilowatt itself is the unit of power. Anyway, let me stop here. We'll recap some of this on Tuesday, and you guys have a good weekend.